time and space complexities of Kruskal's algorithm. In the last lecture, we learned about Kruskal's algorithm, which is used for finding the minimum spanning tree of a connected weighted graph. In this lecture, we have to see what are the time and space complexities of Kruskal's algorithm. In order to find this out, what we'll do is we'll go through the steps that we followed in Kruskal's algorithm, and then we'll see what is the time taken for each step and what is the additional space taken by each step. In this way, we'll be able to find out total time complexity and space complexity of this algorithm. Let us see what were the steps that we followed. First step is to sort all the edges. So you wanted to sort all the edges of your graph. And the second step, I'm only considering the major time consuming steps. You had to iteratively do certain procedures. So one thing is you had to find out whichever is the smallest among all the edges. So you wanted to find smallest edge from the remaining edges that are to be considered. And then you had to check whether there is a cycle formed or not. If there is a cycle, in that case, you cannot consider this particular edge for MST. And if there is no cycle, then you can consider this particular edge for MST. This is what we followed in Kruskal's algorithm. Coming to these steps, first of all, the first step, sorting all the edges. What is the time taken for this? If you want to sort all the edges, you will, let us say, use merge sort algorithm or heap sort algorithm. Whichever it be, for this particular sorting step, you will have to take order of E log E time. If there are E edges for this graph, then you will be consuming order of E log E time for sorting. And when you say E log E, equivalently, you can also say E log V. Why is it so? Why is it that you can say either E log E or E log V when you are coming to time complexity? The reason is number of edges in any graph in worst case can be order of V square. If you are having V vertices for a graph, the number of edges can be in worst case order of V square. When it comes to taking logarithm, log V square can also be written as 2 log V. So when it comes to time complexity analysis, log V and 2 log V are one and the same. So log E in worst case can become log V square, and log V square can be written as 2 log V. So instead of log E, you can also write log V because 2 is not significant here. This is the reason why you can either write E log E, which is the right notation when you are considering E edges. In order to sort it, you will take order of E log E time. But because E is maximum order of V square, you can also write it as order of E log V. So both are right. You can either say it is order of E log E or it is E log V. What is the next step? Iteratively, you are doing certain step. First thing is finding the smallest edge among the remaining edges. So already your edges are in a sorted order, because of which you just have to find the next element in your sorted array, which can be done in order of 1 time. So this step takes only order of 1 time. And then in order to verify that it is whether forming a cycle or not, in this step we discussed that we have to use disjoint set data structure. And if you remember our disjoint set data structure from the data structures lecture series, we learned that in order to do a find operation in disjoint set data structure, considering you are using both path compression as well as union by rank, you will be taking order of alpha of V time, where alpha is your inverse Ackermann function. And what is the speciality of this inverse Ackermann function? Inverse Ackermann function, it grows very slowly that you can consider it as a constant. So even if V takes very, very large values, the value of inverse Ackermann function will be very small values like maybe 2, 3 or something. Even if you are having a very, very large number of vertices, still it will only be 3 or 4, because of which you can consider it as a constant. But the point is, this is amortized time complexity of this algorithm. So the find operation in disjoint set data structure, it has an amortized time complexity of order of alpha of V. But let us say if you don't want to consider amortized time complexity, or maybe if you don't want to apply path compression, still you can do this in order of log V time. So ideally, you can take this as order of alpha of V, but even if that is not the case, you can do in order of log V time. So why is it log V? Because let us say you want to do a find operation in disjoint set. So what are you going to do? You are going to traverse from the leaf of the tree till the root of the tree, that is till the representative element. If you want to travel from the leaf till the root, you have to travel at max whatever is the height of the tree. That will be your time complexity. So what is the maximum height in this case? Considering that you are using union by rank, your tree will be balanced, and because of which maximum possible height when you're having V vertices will be log V. And because of this, your maximum time complexity of find operation will be order of log V. So even if you take it as order of log V instead of alpha of V, still the complete time complexity of this loop will be order of E into log V. Why is this E into log V? Because you are doing this loop E times. E is whatever is the number of edges. Considering that you will be doing E, even if you are going E times into this loop, still your time complexity will be order of E log V. So this will either be order of E log V, or if you consider the inverse Ackermann function, in that case it will be order of E into alpha of V. So either of this will be your time complexity. See, ideally you can consider it as order of alpha of V. The reason I'm okay taking E log V here is that anyway your sort step is going to consume E log V. So you are not going to get a total time complexity lesser than E log V for this particular algorithm. So even if you consider that this step is taking E log V, it is still okay. Time complexity is going to be that only. So what is the final time complexity? It is order of E log V or order of E log E, whichever you want to take. So you would ideally write it as order of E log V because that is a better notation. Okay. So that is it about the time complexity. What about the space complexity? Coming to space complexity, the most space consuming tasks here. One is when you want to sort all the edges. You want to sort all the edges also means you want to store all the sorted edges separately. If you want to store all the sorted edges, that takes order of E time. See, I'm not using the input edge here. I'm mentioning about the storage used for storing the sorted edges. So this is not the input space. This is additional space that is used by the algorithm. Okay. So the algorithm will take order of E additional space in order to store the sorted edges. And then what about the MST? We are building the MST from scratch. So initially you have an empty MST and then you are building this MST from scratch, which means you are adding 1 edge, 2 edge, 3 edge and so on and building the MST. So this will take order of V space. Why is it taking order of V space? Because the MST will have maximum V minus 1 edges. So for each edge, if you add 1, still it will take order of V space. So this is for the MST. One more space consuming part is we discussed that we will be using disjoint set data structure. So for this disjoint set data structure, if you remember from our disjoint set data structure lecture under the data structure series, we learned that there is a parent array which we'll use and also a rank array which we have to use in order to implement disjoint data structure. For this parent array, you have to take order of v space. Similarly, for the rank array also, you have to take order of v space. So the total space complexity will be order of v plus order of e, or you can say the space complexity for Kruskal's algorithm is order of v plus e. So that is considering order of e that is taken for the edges and order of v that is taken for storing the MST and also for the parent array and rank array. So what are the time and space complexities of Kruskal's algorithm? Time complexity is order of e log v and your space complexity is order of v plus e. So this is about time and space complexities of Kruskal's algorithm.